Hello, the topic for today is ML algorithms, and I will take you through the theoretical part first, and then we will get into seeing some actual algorithms. And I will cover today for you the implementation of a few algorithms which I had written in Python long time back. And I will also show you reinforcement learning algorithm, which will show you how a model or a reinforcement learning agent learns on its own about the world by interacting with the world. If you sit back and think properly, you'd be amazed of how a small agent, which is written with just a few lines of code, can learn about the environment it is in, and it can, learn its way around a specific problem. We'll get to that, and I will explain to you. Let's get going with the tutorial itself. For today covers only the topic of machine learning algorithms. So when we say only, we are doing a disservice, because that is the basis of all of machine learning, all of a lot of things, a lot of wonderful things that can happen through machine learning. So we'll cover what's an algorithm, what is machine learning at a high level. We will cover, because that is a topic which can, there are whole books written on it, and you can easily get many good books written on that topic. Then we'll get into how a problem is solved using machine learning. Types of machine learning I will cover, and I will give you two examples hands-on of machine learning, some algorithms, and of course the hands-on, which would be the highlight of this whole session in my opinion. So here we go. So what's an algorithm? An algorithm is basically a number of steps that a computer program must execute in order to achieve something. A very high level sort of explanation of what an algorithm is. So essentially logic that is written in some programming language. It could be any programming language. So some JavaScript, Java, Python, could be many other languages. And the program executes that logic and gives you an output. That is what the program essentially does. In the context of machine learning, the program iteratively executes that logic, and when it iteratively executes that logic, it becomes better and better at doing something, and the output becomes better and better. As per the material of the slide, this is the logic based on which the computer program runs, which is absolutely correct. It is the logic based on which the computer program runs, and we will show you a very simple algorithm on the next slide. Here it is. To print numbers from 1 to 20. So if you look at the flow on the right side, the flow chart, we initialize some variable to 0, we increment that variable by 1, so the count of that variable becomes 1, and then we go down and print the first time. Then we actually check what is the value of x, and if the condition is not met, we keep on incrementing till we meet that condition, and when that condition is met, we jump out of that loop. Okay, so then, having seen what an algorithm is and having seen what a very simple algorithm is, we'll look at the concept of machine learning. So on the slide, you see nice looking, human looking machine reading a book and trying to learn something from the book. Now, is this really machine learning? In the context of what we define as machine learning, this is not what machine learning is. So machine learning is better defined by the lower part of the slide, which mentions that it is a type of artificial intelligence. So machine learning is a subset of artificial intelligence, which provides computers the ability to learn without being programmed explicitly for doing something. Now, if you program a computer to do 2 plus 2 is equal to 4, and you feed the numbers, let's say you program a plus b is equal to c. Now you feed a and you feed b and you get c and you print out c. Is that machine learning? Obviously not. It's not machine learning. But if you program a computer to look at multiple data inputs and then make a statement about the output. So for example, I will give you a background of one of the hands-on that I will show you. You have multiple employees. Each employee has certain specific characteristics about them. So somebody is old, somebody is young, somebody is man, somebody is woman. Somebody lives far from the office, somebody lives next to the office. Somebody has a lot of experience, somebody has little experience, somebody is working with the same manager for 10 years, somebody is just coming to that manager. So there are different characteristics of different people. Now, using these characteristics, can we make a prediction about a specific person? If we can, then that program which will read these characteristics and make a prediction will qualify as a machine learning program, machine learning algorithm. And I will show you the output of a few algorithms with this exactly same example. So in fact, the official definition is a little more complicated than this, and the official definition says that if a program becomes better at a job, at a specific job, when being fed more and more data, then that program qualifies as a machine learning program. So there is a very specific definition which you can look up on Google. It is very easily available. So the original parts of machine learning were established in 1959-60, that period. So it's quite some time, long back. And so that kind of basic definition is widely available. You can easily Google and find out. But essentially what is happening is you are exposing the program to a set of data, and the program is becoming better and better at doing certain job. In this case, the job is about making a prediction about whether somebody will leave the company or not, attrition prediction. So that immediately leads us to the different types of machine learning. And it is important to understand this because a lot of people, and I have worked with a lot of people in machine learning area for quite some time now, a lot of them, even senior people who are exposed to complicated things in life, even they are confused sometimes on these different types of machine learning. So it is important to pay attention at this point, and it's very easy to understand the differences if you pay attention. Okay, so there are mainly three types of machine learning. One is called supervised learning, which is the most common. Supervised learning you will see everywhere in industry specifically. And the second one, and I'm jumping right to the right side, is called unsupervised learning. And the third one is called reinforcement learning. So I will show you an example of supervised and reinforcement learning. Although in industry, reinforcement learning is the least used at the moment. It is very promising, it can do many things, and I'll give you some examples as part of this slide only, but it is the least used at the moment. So let's look at supervised learning first. Okay, so supervised learning is an algorithm that uses a known data set called a training data set, and it learns about the relationship between the input and the output, and then this relationship is learned by the program and stored as sort of knowledge within the program. And then when the new data set comes in, it makes a prediction about the new data set. If that sounds very hi-fi complicated, let me give you a simple example. So I will not go with the example given here. I will give you a simpler example. Okay, let's say you write a program which will look at photographs and recognize whether the photograph is that of a dog or not. So that is a standard program in machine learning, although it is not that easy to write it, but it is nowadays. These kind of programs can recognize objects with more than 95%, 96% accuracy. Sometimes in certain settings, even human beings may be fooled, but the machine learning program will not be fooled. People have reached that level of sophistication. So how do you train the program? You feed that program 100,000 photographs. Each photograph is that of a dog in different positions, from the top, from the front, from the bottom, from the side, with the head tilted, with something in the background. So let's say there's a dog sitting on a sofa. Somebody has to label that as dog, not as sofa. So that is the training that the model does. So the model knows that, okay, when a dog is sitting on the sofa, it's a dog, it's not sofa. When a dog is like upside down with 4 feet in the air, it is still a dog, it is not something else. So this kind of data set is created, and this kind of data set is publicly available. So you can download these kind of data sets and you can train your models. So it becomes supervised learning because somebody is supervising the learning, somebody is labeling the data, somebody is saying that although there's a dog on a sofa set, it is not a sofa set, it is a dog. Although a dog is there with all 4 feet in the air, it is not an inverted something else, it is a dog. Although a dog is behind, let us say, a chair, it is still a dog, it's not a chair. So somebody has to create that data set and then feed it to the model. And it is not always easy to create this kind of data set. And so it becomes a very laborious process sometimes to create this kind of data set and then train the model. So that is supervised learning for you, where you are supervising the input to the model. The example given here is to teach by example, which is a very high level example. That's why I went to a more specific example of a model learning about dogs. It could also be a model learning about human beings. So there are models today which will recognize people's faces, etc. So those are all variations of some sort of supervised learning. Next comes, in the order of life, in industry at least, unsupervised learning. Unsupervised learning is a machine learning algorithm which does not need you to label the data. So, as an example, let's say you have a photograph in which there are many handbags. In the same picture, there are some fountain pens. You also have in the same picture coins. So an unsupervised learning algorithm can automatically segregate these three classes. It will automatically learn that, okay, these are bags, these are coins, these are fountain pens. You don't have to label the data for it. So you don't have to supervise the learning for the model. It will automatically segregate into different categories. This is used in industry. I have used for, segregating different kinds of problems. So if you have problems characterized by specific characteristics, and those characteristics, you need not understand what those characteristics are. The machine learning model will automatically understand that out of this data set, which is let's say 300,000 points, there are 50,000 points which have one kind of characteristic. There are 75,000 points which have a different kind of characteristics, and the remaining part of the data set has a third kind of characteristic. So it will automatically create three different clusters, and it will put each of the inputs into these different clusters, segregating these three clusters, saying these are cases of problem 1, these are cases of problem 2, these are cases of problem 3. So again, a very high level example is given here, but in the machine learning context, an example like clustering is better understood by people. So for example, if you have, let's say you put in the incomes of everybody, the machine learning model could automatically segregate people into medium, high, low, very low type of income. So it can do that on its own, which is the good thing. So you don't have to label the data. Now getting into reinforcement learning. Reinforcement learning is a situation where the machine learning model learns from interacting with its environment. So the software agent learns from its environment what exactly to do in order to get long-term good behavior or long-term reward. So for example, you take the way a child learns to walk. So if you observe how a child learns to walk, he or she will initially make many mistakes, will fall down, but we quickly learn that, okay, when you step like this, you lose your balance and you fall down. So next time, or after 10 such trials, the child will learn and not make the same mistake. Over time, the child will learn how to walk properly, then how to run properly, and how to run fast, and so on. So the reinforcement learning agent can be thought of as such a child type agent, which will learn from interacting with its environment, so that overall, over time, it will learn to do the job properly. There are many examples which we can cite. So a couple of them I will cite here. One of them, let's say an agent which learns how to play chess. Those agents exist today. You can play chess against those kind of agents on the internet. Unless you are a super fine champion, it will beat you, because it would have played that chess game against hundreds of thousands of people already, and would have learned from those games, and it knows how to play chess better than you. Unless you are a world champion level player, you will not be able to beat that agent. So the agent has learned by playing with others, and initially that agent will lose. Initially 10 years ago, when the agent was created, the agent would easily lose and you would be very happy, I'm beating the agent, but the agent is learning from you. And so as it plays against different players, it learns that, okay, these are the best things to do in these circumstances. So over time, it becomes better and better. So that's a machine learning algorithm. It is becoming better and better by playing with different people, by interacting with different kinds of environment. and so it qualifies to be a machine learning algorithm. Now this is a logical breakpoint for us within the program, within this presentation. So there are different types of problems that you can solve using machine learning, which is what this slide refers to. Is this A or B? What you mean is, does this item belong to one class or another class? So it is like the dog problem. So is this picture the picture of a dog, or is it the picture of a cat? So in my case, we are looking at a text-based input, and then we are trying to categorize, okay, does this text belong to one of these 340 categories? A simple example of this could be, you are reading a CV, you make a decision, is this CV worth shortlisting or not? So that is a class. There are two classes. One is worth shortlisting, the other is not worth shortlisting. So your machine learning model could read the CV and could make a decision that, okay, this shortlist this CV, don't shortlist this CV. That's a classification problem. Is this weird? That's an anomaly detection problem. So anomaly detection problems is slightly different from a classification algorithm, because in a classification algorithm what happens is there are many instances of both classes. So if you have 1000 CVs, you'd probably shortlist 100 of them and 900 of them will be rejected. So in both classes, rejected as well as accepted, you have decent numbers, 100, 900. Whereas in a anomaly detection, you'd have very few examples of an anomaly. That is why it is called an anomaly. An anomaly will not come every time. If it comes every time, then it becomes a classification problem. Then it becomes problem number one, not anomaly problem. Anomaly problems are where the anomalous situation comes once in a while, rarely. And so the approach is slightly different than a classification problem. How much or how many, that is a regression problem. And regression, I think I covered last time on this kind of session, where what we try and do is we take inputs about the different items in the set, and we try and make a calculation of the output values. Example, if I tell you that in Bangalore, and I don't know where the participants are from, could be all across the country. So if I tell you that in Bangalore, in a particular area, let's say North Bangalore, if I have a flat which has 4 rooms and is 2000 square feet, can you tell me the price of that flat? That's a regression problem. So your inputs I'm giving you, 4 rooms in a specific location in Bangalore. I'm asking you the output, cost, price. That's a regression algorithm. We could use regression to solve this problem, but we need to train the model, regression model, by giving it data about different houses, flats with different number of rooms and the price of those on the Bangalore market. How is this organized? That's a unsupervised algorithm, which is a clustering algorithm, saying that, okay, this is organized in 5 clusters, cluster 1, 2, 3, 4, 5. What should I do next? That is a typical reinforcement learning situation where the agent is learning from its interaction with the environment, and it is saying that, okay, if I do this next, I will do better in the long run. It is like taking a decision in your real life also. So for example, today, if you decide, you have 2 options. Should I go and watch a movie, or should I go to the restaurant and eat something? Which would be better in the long run? So that decision you take based on your experience and based on your environment, that kind of situation. So I'm giving you a very everyday type of example, but it is parallel to what a reinforcement learning algorithm does. It takes a decision. Okay, next I'll do this, and I'll not do the other 3. These kind of problems can be handled with different algorithms. So there are many algorithms you need to learn. It will take years to do a proper job of it. So don't be in a great hurry. Work in the area of your interest and learn in your area first. And you'll automatically find that you become more and more interested. If you have that inclination, you'll become more and more interested, and you will learn more and more algorithms over time. So a classification example is given. Is it cold today? Is it cold? Yes or no? So depending on yes, no, maybe, you will take a decision of whether you will go to work or not. So if you have only 2 classes, so let's say your decision is go to work or not go to work, that is called a 2-class classification, which is generally common. Will this happen or not happen? Will I go to office or not? Will I watch the movie or not? That kind of thing. So that's a two-class classification. If you have more than two classes, it's called a multi-class classification. So you have three choices, four choices. Let's say you have three choices. I could go to the movies, I could go to a restaurant, I could sleep in the afternoon. So three choices you have. If you are making one choice or one classification based on inputs, so let's say it's very, very warm outside and it is raining outside. In that case, you may decide that, okay, given the circumstances, I will take the third choice of sleeping in the afternoon. That's a multi-class classification because you have more than two classes or two choices. So you can classify. Usually you'll see this in industry, accept, reject type of thing. Accept a CV, shortlist it or reject it. That's a two-class classification. You could also have multiple classes. Like in an appraisal system, you'd say very good, good, not so good, absolutely bad. Four classes. So four-class classification. So you could use a machine learning algorithm to do that classification also, provided you provide that algorithm proper data and you train that properly. Otherwise, your output will be all erratic. So anomaly detection algorithm is a very nice example given here, and it highlights both the points which I was talking about. If you see this anomaly, how many anomalies do you see here? You see only one out of so many. So anomalous situations are few. They don't occur regularly. They occur once in a while. An anomaly detection algorithm could be used to detect that it is not common. So if you, let's say you use your credit card and you use it for 2000 rupees, 1000 rupees, 1500 rupees, that kind of transactions. One sudden day, you decide that, okay, I will buy a laptop using that credit card, and you spend 35,000 rupees on that card. What will happen? You may get a call from the bank or the credit card issuing company saying that the card is being used for 35,000 rupees, because in their data, in their past data, you would never have used the card for 35,000 rupees. And so an anomaly detection algorithm will immediately flag that that is not the normal pattern of your usage. Whereas another guy who uses the card for buying air tickets, buying different high value items, will not get that call if he or she uses that for 35,000 rupees, because for her or him, the credit card usage pattern is like that: 35,000, 50,000, 40,000. It's okay. That's the usage that he or she has. Then regression algorithm. This is the easiest, probably the first algorithm people learn, which is about giving multiple inputs and finding an answer or a value. So very good example would be something like the price of a house, given that it has certain square feet, it has certain number of rooms, and it is in a certain location in the country or in a proper city. So with these inputs, can you calculate the numeric value of the output? That's a regression algorithm. So here, if group A, group B, group C, this is like the typical KNN type of algorithm, which looks at what are the nearest neighbors and clusters nearby neighbors together, and it says that, okay, this is group A, this is group B, this is group C. So this is how your data is organized. Your data is organized in 3 clusters, and the algorithm can tell you this is cluster 1, cluster 2, cluster C. Now, if you have domain knowledge, you can go in and check and say that, okay, cluster A looks like bad performers. Cluster B looks like performers who are very fast at their job. Cluster C looks like performers who rarely come to office. Depending on the specific problem that you are handling, you can decide on what these clusters represent, because the algorithm will not tell you what these clusters represent. It will give you a label, level 1, 2, 3, and you have to figure out what level 1, 2, 3 means based on your knowledge of the situation, of the domain, etc. Yeah, so the example given is also the same examples given as system which plays chess. Temperature control system, which is even easier to actually make, which decides on what temperature should be set, should it be increased or decreased. Automatically the thermostat will be changed based on input. So if you never change the temperature setting, let's say the temperature is set at 24 degrees and you never change the temperature setting from 24, then the reinforcement learning algorithm will learn that, okay, for this setting 24 degrees is okay because nobody changed it. Now if it is set at 20 degrees and somebody keeps on fiddling, increases it, decreases it, then the algorithm will learn from that fiddling, that is the environment. You are fiddling with the thermostat setting, and the algorithm will learn that, okay, 20 is not the right temperature. So most of the time people are increasing the temperature towards 23, 24. So it will learn that okay, 20 is not the right temperature. I should go and keep it at 23, 24. So if the temperature falls to 20, it will increase it to around 23, 24. If the temperature rises to 28, it will decrease it to 23, 24. It will learn automatically without human guidance, but it will learn from the inputs that people give the system. So if you keep fiddling, it will learn. Now suppose you are like, hypothetical example, we are in a group which likes high temperature and you keep the setting at 27, let's say. Then it will learn that 27 is nice temperature for these guys. And it will try to keep the temperature at 27. And if you have guests who are from, let's say, a different region, let's say if they are from Europe, and at 27 degrees they will be sweating, then say it's very warm, it's very uncomfortable, etc. But the system would have learned from you earlier that okay, 27 is the right temperature. It will keep the temperature around 27. The reinforcement learning algorithms will work like that. So we come to a sort of recap of different algorithms. So there are many algorithms. Some are given here. So supervised models, regression falls under supervised models, linear regression, polynomial regression. So this is usually done for calculating an output given multiple inputs. So a house has 4 rooms, it has so many square feet, it is situated in such and such city, it is situated in this part of that city, what should be the price? So given these inputs, can you calculate the price? That is regression. Decision trees, they are for taking classification. So we have decision trees, we have random forests, we have many other classifiers for classification. There are many, just a few are mentioned here. In classification, KNN, trees, logistic regression, knife base. Knife base could be used for anomaly detection too. Support vector machines can be used for classification. There are others also. There are deep learning models which could be used for classification. Indeed, most of the picture-based or text-based models that we use, they're all deep learning models which are not mentioned here. But there are many algorithms that we can have. Unsupervised, PCA, K means K nearest neighbors, they could be used. Association analysis, I am not so familiar with that area. Hidden Markov models, they are used more in the reinforcement learning domain. And reinforcement learning could be done for continuous situation or episodic situations. Episodic situations mean that a certain situation starts and has a certain end. So for example, a chess game has a start and an end. So a game has a clear-cut end and a clear-cut start. So that is called an episodic situation. Continuous situation could be like your air conditioner, which is continuously running 24/7, and it never has a clear-cut end. It never has a clear-cut start. So it is just like a process running always. Reinforcement learning could be used in either type of situation. Now I will show you 2 examples of hands-on. One, I will train and run the model in front of you. And the second is a reinforcement learning model which takes some time to train. So I've already run it, but I will show you the output and I will show you how the model learns about the situation. Okay, so what I'm trying to do is I'm trying to predict if specific employees will attrite or leave the company based on certain inputs, based on 15 input factors, and I'll show you the data set. This data set is publicly available and it was uploaded by IBM. So this data set was probably part of some of their studies, and later they would have done something more sophisticated, so they allowed this data set to go public. Of course, they have removed the names and all that. So this was written mid 2016 by me, and what I tried to do is I tried to use the data and run different supervised categorization models on this, classification models basically. So the classification model basically is a two-way classification here. The output that I want to understand is whether given these inputs or given this background, whether the person will attrite or not. So 2 classes, will attrite, won't attrite. So 2-class classification. And here is the data set. The original data set, so there's the age of the employee, whether he or she has attrited or not, does he or she travel for business, what is the daily rate for that person, which department does he or she work, what is the distance of office from home, what is the level of education or years of education, what is the education field. And this employee count doesn't matter because this is one for every row. Employee number, Environment satisfaction. So your first job is to look at this data set and understand which are the useful parts. So there are some which may be useless. This is not very useful. All the points are 1 1 1 1 1. So we can get rid of this. Employee number, also not very useful. Your employee ID is not going to help me make a prediction about whether you will stay or not. Environment satisfaction, yes, important. How satisfied are you with the environment? Gender may be important, I don't know. Hourly rate may or may not be important. Job involvement, probably very important. Job level, yes. Role, satisfaction, yes, important. Marital status, definitely important. Single people can move at the drop of a hat. Monthly income, important. Then number of companies worked for, may be important, may not be important. All of them should be over 18. If there is a no here, then we have to drop that person from the data set and ask HR why you recruited the guy or girl. What was the percentage salary hike last year? What was the performance rating given? What is the relationship satisfaction? So this may be very subjective and we may decide to drop it. How many hours does he or she work? Stock options, do they have it? Total working experience. What was the training time last year? Does he have good work-life balance? How many years working at the company? How many years in the current role? How many years since he was last promoted? How many years was he or she working with the current manager? All of this information here. So if you see, there are 35 columns in this. So of these 35 columns, we have done some sort of a first cut understanding of, okay, what is important, what is not important, what is very subjective. So for example, the relationship satisfaction may be very subjective, and so it may not help. And so we have dropped these kind of things. And if you see the real data that we have used, so then there's a data definition. What does each mean? Low, high, good, bad, whatever, ugly. And then the data for analysis scaled. Scaled means we have the original data looks like this. Age was 42 for the first guy, right? We scale this in order for machine learning algorithms to work better. And if you go through a machine learning specific algorithm course, you will understand that why we do that. So we scale the data, and if you see, we have scaled it here by dividing each data set by the range of that data. So for example, here we have gone for data for analysis R2 $2. So if you look at this formula, this is the max minus the min, this is the range. So by dividing by the range, we have normalized. So somebody who was 41 years old, in the scaled data, this will look like 41 by 42, 0.96 something, 0.976. That is the first person. 41 divided by 42. Similarly, if the person were more than 42, it would be 1.1 something. So it is all scaled. All of the data gets scaled. So after scaling, because this is formula, we have then copied and pasted it here as only values. So these are only values. Now we go to the actual program, and I will just restart here. Restart and clear output. Okay, so we have restarted this. I'm running on Jupyter notebook, which is useful because it is a web-based thing. I'm running it on my machine, so you see localhost 8888 and so on. You can run it on the web also. We are importing the libraries here, and we are importing some graphic libraries, and then we are importing the specific libraries which will do the calculations. So train, test, split. It splits the data into two, train and test. So we don't give the test data to the model to learn, and we only train the data on the trained data, and we test the data on the test data. Then we have one by one imported. First we imported logistic regression because we want to do a classification. So we imported logistic regression. We read that data from the Excel file. So attrition underscore ML underscore data.xlsx. And from here, we have gotten into data for analysis scaled, etc., etc. So then we have done a very complicated method of getting the data into categorized data. So there are much simpler ways of doing it. It was written in 2016, so I wanted to do it from scratch. So I've done it from scratch. There are libraries to do this now. And I will just run it, and I will show you the output. It started running. So reading the data will take some time, few seconds. Yes, the rest goes very fast. After reading the data, the rest is very, very fast. And what we have done is at the end, I have put a table together. That is to make a comparison. So this is the table. So logistic regression, which was the first one, what was the accuracy? 85.8. Linear discriminant analysis LDA 84.3, Gaussian naive Bayes 79.6, support vector machine 84.6, K nearest neighbors 84.3, random forest 85.03. So it seems that the simplest algorithm, logistic regression, is doing very well, 85.8, and random forest is also doing pretty well, 85.03. The others are not doing that great, 84.79. Gaussian naive Bayes is doing the worst of all of these. So we choose to do this, run with this, and if you see any of the models being run, you'll see this random forest has been, that is, we are appending in order to make the table, but if you see how the model runs, the model is fitted on the trained data. So you see clf.fit. CLF is just the name of the classifier, random forest classifier. You can name it something, whatever else you want. It is fitted on the trained data, and the prediction is always run on the test data. It's never run on the trained data, because you don't want to predict on the trained data. You want to predict on the test data, which the model has not seen yet. And then there's some printing going on, 85.03, and that is finally appended into a list, and then the list is printed out. This is how the thing looks like. So this is a very simple example of classification. So we are classifying with 85% or 86% accuracy. We can classify that whether the person will leave or not, given these 15 inputs. So we have taken 15 inputs out of the 35 that I have shown you. We have taken 15 inputs. If you can see here, 16 inputs actually, 16 columns, 1470 rows are there in that data set. So attrition data frame dot shape. This is the shape of the data frame which is being read from the Excel sheet. Now I'll quickly go through the reinforcement learning thing. So this here you see, with very little data, you are able to make a model which will make predictions with 86% accuracy, which could also be improved. I have not really spent too much time on trying to sort of optimize it. So the problem is this. The problem is that the agent has to go from here to here, from start to the goal. And there is a barrier here. The agent can do only 4 things: left, top, right, bottom. If by going bottom or going right, it hits the boundary, it remains in the cell, in the same cell, and it doesn't get any reward. If it gets to the goal, it gets the reward. So if it gets 0 reward, it knows that, okay, I haven't done something very great. So it will automatically learn the path from S to G. Now 2 things I'll show you. I'll not show you the intermediate because there's a lot of code and there are a lot of things happening, but you just see the output, you'll see. So there are 2 parts of the problem. So earlier there was a barrier, and later what happened is we opened this, we broke the barrier here, and we tried to see whether the agent will learn that it should go this way, because this way is shorter to the goal, this way is longer, this way is shorter. So after some time we broke this barrier to see whether it will learn that, okay, now there is a new path available, the better path, shorter path available. Leave all these graphs, you can see this one, last one I'll show you. Yeah, here. So initially when the barrier was here, it was going like this. You can see the visitations. So this shows you how many times each state was visited. The more towards yellow it is, the more times it was visited. So it started from here and it went like this. So it definitely visited these states a lot of times, yellow, 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 because it has to pass through this. It cannot pass through any of these because there's a barrier here. And then it went through this path and then went like this. This is the path it chose. And after the barrier was broken, look at what happened. It did not go through this path at all. It learned that, okay, there is a shortcut available here. It went this way. So what was yellow here, which was most visited, became blue, and these became deep blue. It never visited these states. This path it never took. It automatically took this path. So it learned, the reinforcement learning agent learned that earlier I wanted to go this way, but now there is a shortcut available and I will go this way. This is the shorter path. So I will get the reward quicker. So this is an actual reinforcement learning agent being applied on a very simple problem of going from one point here to here. These can become more and more complicated. So for example, playing chess, making a robot to learn how to walk. And there are other examples also, making, calculations, or what is the best thing to do in the bond market, when should I buy, how much should I buy, so on. So those kind of applications are there. So that is how these things work. And this is, I just did not run it because I can run it, but it will take 15 minutes to run because of the number of calculations required. So it will take some time to run and learn. So I ran it just before the program actually started. So this is how an algorithm works. So the algorithm here, in this case, the algorithm was written like this at the top. This is called a DynaQ algorithm, dynamic planning and Q learning, both combined together. So it says initialize Q. You remember the flow chart we had shown you for simple printing 20 times. So this is like that, but it is more complicated because we are trying to do something more complicated. So we started with some Q list and some model which is showing the state. State means where is it in that grid and what is the action to take, SA. So put S as the current non-terminal state. Whatever state you are in, put that as S. Then choose the action based on a particular algorithm which is called epsilon greedy algorithm. It's basically an algorithm which will try to take the best action, but once in a while it will try and explore whether other actions are better than the best action or not. That's why it's called epsilon greedy. So it's greedy, which means that it is trying to take the best action which it knows about, but it is also exploring sometimes, epsilon times. Epsilon is a small value. Take action A, observe the result. That is the typical reinforcement learning. Take an action, observe what happens. So when that happens, you update your current state's value, which is called Q learning. So this loop repeats multiple times and these values keep on getting updated. So that is all we are doing in this entire code. From the top to the bottom, we are doing only these few steps, these 5 major steps. And the results are what you saw. So the agent learns how to move from point A to point B. It also discovers that a new shortcut is available. This is an example of a reinforcement learning algorithm. Okay, thank you. Bye.